Hi, I'm Yadvendra Yadav. I am software architect at IBM. And today I'm going to talk about, the read performance strategies for workload using EBPF. The agenda is we'll have an introduction of EBPF, then we will try to understand a little bit of inner working of the EBPF and why EBPF is a best choice to extract the data from the kernel. At a high level, we will touch upon the Linux kernel read-ahead strategies, mainly how the read-ahead works in the Linux kernel, what are the interesting points in the kernel from where we should fetch the data. And then we will try to, so whatever the data we will collect from the kernel, we will try to give it to the AI models, where AI model can help us in suggesting what should be the best practices, where the workload is going wrong, how we should change the workload, and certain things like that. And in the end, we will have a demo for that. So what is EBPF? So EBPF is a kind of a revolutionary kernel technology. So typically what we can do is we can put a custom code in the kernel, and that can be loaded dynamically. The good thing about the EBPF is that since we are putting the code in the kernel, we have to verify that the code doesn't cause any negative impact in the kernel, like kernel crashes and all. So the BPF is having various mechanisms, to verify that whatever code we are putting in the kernel is proper, we are not doing any wrong memory access or invalid memory access, and even if we are having some loops in our EBPF custom code, those are finite loop, not an infinite loop. So the BPF actually stands for Berkeley Packet Filter. Initially, it was used for the filtration of packets. And if we see the TCP dump, whenever we try to filter a packet at a very lower layer in the stack, the TCP dump actually, hooks the BPF program. So the filtration happens at a very low layer for the performance reasons. So here is a simple example where where TCP dump is trying to filter IP packets. However, later, this technology was extended for other subsystems also. For example, security, observability. Since we are hooking something in the kernel, right, we can always hook certain code in the kernel and try to observe what is happening there. And moreover, initial BPF has a less number of registers and, less instruction sets and all. And later on, extended BPF was having the large instruction set, the register size got increased, and the number of registers also got increased. So here is a simple example. You can see that we are hooking the EBPF program at the syscall layer. So whenever the exec ve6 syscall will be executed by the process, this particular program will get triggered, and it will try to get the PID and the name of the process and put into the perf buffer. We'll talk about these in more details in the coming slides. So this is another version of the same program. So if you look at the program on the left-hand side, you will see that there is a program, there is a function called hello, and it is a plain C function. And this is what is called the BPF program. So you can write the BPF program in a plain C language. So here, what we are trying to put is we are trying to print a string hello world into the Linux kernel trace buffer, which is a ftrace buffer. And later on, we call the BPF. So internally, this BPF call, what it will do is it will invoke something called as a BPF system call, and it will compile this program into the BPF bytecode, and then this bytecode will be loaded in the kernel, and the kernel, inside the kernel, the BPF runtime has provided something called as a verifier. So the verifier will verify this particular bytecode for invalid memory accesses and all, and once all goes fine, what will happen is this particular BPF bytecode will be converted into the native instruction set based on the architecture for performance reasons. And so now, whatever our BPF program was there, it is loaded in the kernel, it is sitting in the kernel. But how to trigger it? So there has to be some events which needs to get attached to this BPF program. So these events can be anything, It can be the trace points, K probes, K-read probes, U probes, So here you can see that after that we call something as attach K probe. So the attach K probe will actually attach an event to our program. So whenever this exec VE system call will be executed, the event will be triggered, and that will invoke our BPF program to get executed. And in the end, we are trying to print the trace buffer. Now, I little bit touched on this, but you can say that, okay, the K probes, the hooking mechanism in the kernel was already there, right? We can write a kernel modules using K probe and hook in the kernel. Yes, it is there. But if something goes wrong in the kernel module, the kernel can get crashed, the system can come down. So the BPF provides a kind of a mechanism where the verification on the bytecode happens. Moreover, the BPF is a kind of a very restrictive environment. You cannot access the kernel memory by just dereferencing it and all. You have to go through the helper functions. So BPF provides you an helper functions. You have to use those helper functions to access the kernel memory or any other kernel function. So it's a kind of a restrictive environment in which you will execute your program, and the verifier makes sure that whatever we are executing is safe to run in the kernel space. So we know that we can put our own custom code in the kernel. We know that this custom code can be attached to an event. Now, when our custom code gets executed, triggered based on the event, we might need to collect the data, So how do we do that? So the EBPF gives us certain mechanisms which are called as BPF maps, where we can store the output of the BPF program into this map, and these maps can be accessed from the user space in a very efficient manner. So at a high level, you can just think of these these maps are sitting in the kernel memory, and they're memory mapped to the user space. So they're highly performant. So some kind of maps I have put here. There are other maps also in the eBPF. So we can have the hash tables, arrays, the LRU list. So when I say LRU, so the hash table are having some limit. So whenever we hit the max entries, the LRU will come into picture, and it will remove the least recently used. We can have a ring buffers and the stack trace to fetch the stack trace from the kernel to the user space. And there are various mechanisms to have a synchronization over these maps. So you can have the maps per CPU based, so that you need not to synchronize the maps for each parallel thread. And in case you want to have a centralized map, then the BPF also provides a kind of a spin lock kind of mechanisms which we can use. So this is another version of our previous program. So now we have attached the event. We have attached our bytecode, the BPF bytecode, to an event which is kprobe. And then we are having a perf buffer with us. So if you see, we have opened the perf buffer, and there is some function like print event, which will be called whenever something comes in the buffer. And then we are polling on that buffer. So whenever something comes in the buffer, our callback will get executed, and we can print the data. So how this entire thing works, So typically, in the BPF, when you write a BPF program, you will have a various sections. It's visible, right? Yeah. So if you see the BPF program, it will have the various sections. So if you see here, there is a section called as maps. So these are the BPF maps I have talked about. Then there is a section here which is the trace point. TP stands for trace point. So I'm putting a BPF bytecode at the trace point, which is schedule process exec. This trace point will get executed whenever we execute a process. So this is one section. Then another section is the trace point when we exit from the process, right? So that is schedule process exit. What happens is, so this is the C program, and these sections, each section is a BPF program in its own. It's a BPF bytecode. So when you compile this program, each of these sections will have a separate section in the binary ELF. So there will be a separate section for each of these hooks. And those sections in the ELF will contain the BPF bytecode, the actual BPF program. So typically what will happen is you will have your C program. This C program will be converted to BPF bytecode. And then later on inside the kernel, this bytecode will be converted into the architecture-specific instruction set for running the program in a more performant manner. Now, I have put here a limited C because there are certain things which we cannot do in BPF program. You cannot have an infinite loop. You have to have restrictions. You cannot call all the functions in the kernel. You have to go through the BPF helper functions. The way to have a global variables is little different in the BPF. So certain restrictions are there to write a BPF program. And how to create the bytecode. So the bytecode can be created using the CLang compiler. So when you are giving your program to the CLang compiler, you can say the target as BPF, and the CLang will create the object file which will have all these bytecodes in the ELF sections. So we'll have a little look at that also. So I said that the BPF bytecode gets created, and then it gets loaded in the kernel, right? So now this is happening in the user space. The bytecodes gets generated in the user space. How it gets loaded in the kernel, right? So there are the system calls which has been created. The BPF is a system call, and using the system call, these programs, these bytecodes get loaded in the kernel. So either you are creating a map or you are loading the particular bytecode for let's say kprobe event or the trace points events. So a short demo for this is, so you can see here, I'm having one BPF program, as I showed you. It's having all these sections. So I have put the kprobes on some kernel routines. So these are the sections in the BPF program which we have written in the C language. And after compiling through the CLang, we will get the object file. And if we see this object file using obj dump, so this is actually the bytecode. So for every you are seeing these bytecode instructions. These are BPF bytecode. And when you run this program, so let's see what happens. So we are collecting the strace output. And you can see, these BPF system calls are getting executed. And there is the system call for load. So we are trying to load, the trace points. We are trying to load the kprobes. And the trace points, there is the kprobes, and then the link happens between your program and the event. So the event is kprobe, and you call the link create to create that link in the kernel. Now, one of the very important feature of BPF is something called as core. Now, what does core means is compile once, run everywhere. Now, this is a challenging problem. See, we are trying to access a kernel data structures, and kernel changes, right? Whatever I'm having today might be different tomorrow. So how I can make my program, at the end, this BPF bytecode is actually sitting in the kernel accessing various data structures. So how can we make it work on on the different kernel flavors, right? So this is done using certain modules, and the first module is BTF. The BTF stands for BPF type format. So typically what happens is, using BTF, we get the data structure layout of all the kernel data structure we are accessing. What is the type of the data structure? What are the member? What are the types of the member? Where they're residing? What are the offsets from the starting of the structure? So all these information is captured in the BPF using byte BPF type format. And it is not, in fact, at the data structure level, but also at the functions. What is the prototype of your function? What is the return type? How many arguments your function is taking? What are the type of those arguments? All this information is captured using BTF. Now, how does the BTF captures this information? It needs certain components. The first component it needs is kernel headers. So you need a lot of kernel headers to get all this type information, but you include one thing, you have to include another kernel header, you have to go in the chain to get the entire picture of your data structure layout. And BPF has made it little simple. It creates a big header file, which is called as a vmlinux.h, and it contains all the types of the kernel. So the BPF is having the knowledge of all the data types which we are going to use in our BPF program using this vmlinux.h. Now the next component, next module, which is required for this core principle is compiler support. So typically what happens is all this type information has to be captured somewhere in the object file. So what the compiler does is that along with the BPF bytecode, it also captures the relocations, the core relocations, which actually contains the information of the type. So there will be a section in the ELF where you can see that, okay, this is the type of the data structure, this is the offset, and what are the type of those members. All that information is captured in those relocation entries in the ELF. And the next module is the library support. So I have compiled my BPF program in one kernel, right? And now I am taking it onto a different kernel. So when I am trying to load the BPF program, there is something called as a BPF loader, which comes into picture. And this BPF loader, what it will do is, it will see that, okay, this is how the data member type format looks when you compiled it, and this is how it is looking now. And is there any difference? For example, there is one member whose offset is changed in the data structure. It has moved by 4 bytes. Maybe some integer has been introduced. So that loader will dynamically change your bytecode before loading it into the kernel. So that is how the core, the compile once run everywhere, is getting achieved. Now, there are certain cases where it will not work. The data structure itself is removed, or the member itself is removed. So such kind of things are not tackled, but to a certain extent, we can achieve, the core principle here. And then there is something called as a BPF skeleton. So typically, we don't want to do all these things on our own at the user space. So the BPF has provided a kind of a skeleton where you can create this skeleton from your object file, and you can just call the APIs exposed by that, like open, load, attach. So the things becomes little easier. So this is very important, when we are trying to extract information from the kernel, because we want to write a code once, and we don't want to change it for every kernel. We want EBPF runtime to help us in that. So typically, how the core works is, at a high level, I'll explain. So here you can see that there is something called as a BPF probe read kernel in the upper half. So this is a basic routine BPF helper function used to read the kernel memory. So we are reading the kernel memory here. But if you see, the core equivalent of the read is BPF core read. And the difference is, it is calling BPF probe read kernel, but there is one macro assigned to it, which is built-in preserve access index. Now what this does is that based on this attribute, the compiler not only will create a bytecode for your BPF instruction, but also it will store the relocation. It will create a relocation entry containing the byte format, BTF format for that particular source. So with this into picture, let's at a high level glance what the architecture flow. So you had the C program, we wrote the C program. The C program we compiled using CLang. We gave the target as BPF. What will happen is a bytecode will get generated. Remember the sections, each section is a separate BPF program. They're not related, they are separate, right? Because they will be triggered by those particular events, whether it's tracepoint or kprobe. So you will have a different BPF programs, bytecodes there. And you might need maps and all to store the data. So once this is done, you will use some kind of a library to load the program in the kernel. So when I say library, it is doing all those things. It is calling BPF system calls to load, create, and then it is doing all the core, compile once, run everywhere. So it might change your program before loading to the kernel to adapt to the target kernel. So then the syscall gets executed. You come in the kernel space now. The first thing happens in the kernel space is verifier. So verifier will verify your BPF program, whether there are any infinite loops, whether there are invalid memory accesses. All these things will be verified in the verifier domain. And once verifier is sure that the bytecode is proper, it will give it to just-in-time compiler. And JIT compiler in the kernel, what it will do is it will convert your BPF bytecode into machine-dependent instruction set. And this is done, for performance reasons, so that you can natively execute the instructions without going through some interpreter kind of thing, right? So now your program is ready. Then the next step is you will attach this program to an event. In this case, we are attaching it to the syscall. And then when that event gets executed, your program will be triggered, and it will output the data into some maps. And once the data is in the maps, from the user space, you can pull the data and fetch the data. And this is the mechanism we will use for the read-ahead strategies, to collect the data at various stages in the kernel. And, we will try to pull that data, create a data sets out of it, and we will use the AI also down the line to give us the suggestions. So let's try to understand a little bit about the Linux kernel read-ahead. The reason is we have to identify the places where we have to hook in the kernel for seeing what is the current read-ahead strategy, how the read-ahead is working in the kernel right now. So typically in the kernel, what happens is that initially, if you see the left-hand block, there's nothing in the page cache. You try to access the page fault will happen, and in the kernel, what kernel will do is, the kernel will call something as a page cache sync read ahead. So kernel thinks that for certain time that you're gonna do a sequential, sequential read kind of thing. So it will do a sync read ahead, and it will try to bring certain pages from the backing storage to the kernel page cache. And this is decided, this window, how much pages has to be brought in, can be decided by what is the request for your read, or it can be tuned also based on certain read-ahead parameters in the proc file system. So now you have got the pages in the cache. That is the second block. Then what kernel does is it kinds of create a marker in the cache saying, which is something like a async size, and there's a marker like PG read ahead. So kernel says, so the way the kernel makes predictions is that, okay, if I reach this marker in a sequential manner, my predictions were right? So when the kernel reaches that PG read ahead in the sequential manner, the kernel says, okay, my predictions were right. So you are reading in a sequential manner. Let me fetch more pages for you in the asynchronous way now. So you can see there are 2 more pages left in the cache, but in the parallel, the kernel starts the asynchronous read ahead. And this window of the read ahead will keep changing based on how accurate the predictions are. So if we are reading it sequentially, might be the kernel will read double the page sizes next time. So the important routines are here are sync read ahead and the async. These are some other level of routines. So I have talked about page cache sync read ahead and page cache async read ahead. But then there are some other type of read ahead mechanisms available in the kernel which are called as advice. So we can use like POSIX advice, madvise calls. So I know that I will need 4 kilobytes of data from my file from, let's say, starting offset is 0. So I will tell the kernel using these calls that, okay, from this till 4K, fetch me the data. So kernel will not do any heuristics there. So it will just do a kind of a force page cache read ahead, and it will try to bring all those pages into the kernel page cache. And if you see here, either we are going through the sync read ahead or the async read ahead path. Both paths will converge in kernel at some API which is called as on-demand read ahead. This on-demand read ahead function is having lots of heuristics where it decides what should be the read ahead window, from where the read ahead window should start and all. As I told you, if the kernel thinks that the heuristics are going right, we are reading sequentially, so might be it will double the read ahead window for the next async operation. And at the end, this all thing goes to the do page cache read ahead, which actually calls the file system read pages or the folio pages, folio kind of routines to get the data from the backing store into the page cache. So we know now how to get the information from the kernel in the effective manner using BPF, right? And we kind of know that what all are the interesting points in the kernel from where we should fetch the data for read-ahead strategies. So what we're going to do is we're going to hook the EBPF programs at these all places, and we'll try to collect the data from them. Now we have a data with us. We have a various data sets. So what we will do later on is that these data sets will be fed to the machine learning models, the AI models, LLMs. And we're going to tell LLM, that, okay, so we have a demo of this. So we will tell LLM that, okay, this is how the data structures are looking. These are the meaning of the data structures. This is the algorithm. So if you see the page cache file in the Linux kernel source code, they have a very detailed algorithm written there, how this read ahead works. And this entire algorithm we can fed to the LLM. The LLM will understand that, okay, this is how the decisions are taken based on that. So what we do is we put all these data sets along with the information, how the kernel is interpreting those data sets. And we will use something called as a RAG, which is called as a retrieval augmented generation. There are lots of talks which has happened on RAG. So using our prompts and then this context, we will send it to LLM, and we'll get we will get a response from LLM, where LLM will give a kind of analysis on the logs, plus what are the suggestions from it. So let's have a look at the demo. So before starting, there was some read-ahead, BPF programs already available in the open source. So I have modified those programs as per the needs to collect from the different places other than whatever is mentioned there. Yep. So if we see here, this is a BPF program, and what we are trying to do is we are trying to find what all are the read-ahead routines in the kernel. So both async and sync routines actually converge to something called as a page cache read-ahead order. That is a common routine which both sync and async calls. So we are putting the things there. We are putting the hooks at the allocs, wherever the pages are getting allocated. Then I told that there is another way to get the read ahead, that is forced read ahead using advice and madvise calls. So we put the probes into those particular routines which will be hit by those advice calls. And we kind of create a window here, that when I am in the read ahead, what all allocations are happening, page allocations are happening, and that's why these maps are created. Then there is something called as on-demand read ahead. And, we also put, so this is where we try to collect the statistics when we allocate a page. So we are in the read ahead window, and in the read ahead window, we are allocating a page, and we try to get the timestamps, when these pages were allocated here. And we put it into some kind of map, and these maps will be showed in the user space as a histogram. And then we also see when this page got accessed. So we have allocated in the read ahead window, we allocated a page, and when the page got accessed. So we get these timestamps, we try to find the difference, when it got accessed, and we will get a kind of a heuristics, how the page cache is getting accessed, whether the unwanted pages are sitting in the page cache for a long time or not. And then I showed you the on-demand read ahead. So this on-demand read ahead will collect all the statistics of the read ahead states into the ring buffer. So whatever it is, read size, whether there are any misses, async size, all these things are captured into the data set. So I'm running a workload. It's a read-intensive workload. I just want to profile this particular workload. So we are having a filters in the program. So once this EBPF program runs, we will get a data set with us. So this data set will look something like this. So it is having all these statistics, how the read ahead window was going on, how we are reading it, what was the start size, how much we read ahead. So you can see that the size is 4, then size is 16, that size is 64. So it's a kind of, it suggests that we are doing a kind of a sequential read, and the read ahead strategy is working. But then we are having the histograms also, and what we will do is that we are having this the chatbot. So we are using LangChain, and for embeddings, we are using the sentence transformer for creating the embeddings. The GPT-4 model we are using, and that's the prompt here. So we are telling when we are sending a data to the LLM, we are telling that you have to understand the page cache. So you are AI assistant. And then we are giving him the entire detail. So this is just a kernel code we are putting here, which contains what are the structure members, what does each member means. And then we use a kind of a few short prompts, which means we give a couple of examples to the LLM that, okay, this is how the data will look. We will put the context, which will be actually our data set, and the history, so that we can chat with our bot, and the question, whatever we will ask. So we are using the LangChain. We are creating a prompt template, the conversational buffer, which will keep all the history. And then we create a kind of a pipeline, the retrieval QA pipeline here. Once this pipeline gets created, we ask question from this pipeline. And so this is how we... and this is the front end of the chatbot. We are using Streamlit for the UI stuff, and it will do the initial level of analysis on the logs, and then later on, we can ask further questions on the analysis. So let's run this. So what is happening now is that when we started it, it went, got the proper data set, whichever we are looking. Once we got the data set, it puts the data set into the context of that prompt, whichever we have written. And this together is sent to the LLM for the further analysis. And now the LLM is providing the analysis of the logs. So so maybe I will come little later here where the analysis. Yeah. So let me pause here. Yeah. So it is kind of saying, that in this particular case, the read-ahead strategy seems to be over-aggressive for the current workload pattern of the application. While it does provide some pages quickly, but there are significant number of pages that are not accessed until much later. And how does this got the information is from those histogram? Because we know the time spent between the alloc and access. So it knows that there were some pages, the read-ahead strategy was over-aggressive. We were trying to bring more pages into the cache and which were not utilized. So it can lead to memory wastage of page cache, because we are keeping the data which we are not requiring, so the new data cannot come. And then it gives a kind of a suggestions to us that you can see maybe we should use POSIX fadvise will need attribute and give it the offset which we really need instead of giving the large offset. And then we should use something as POSIX fadvise don't need, that once you're done with those pages, you call this to flush those pages. And this is how we can extract the insights from the data which is collecting from the kernel using BPF. Yeah, so this is what I wanted to show. The floor is open for questions.
So did you apply this advices run the tests again and make analysis?
Sorry?
So the question is, did you apply these advices given by LLM
Yeah.
to code?
Yes. Yes.
Okay.
So
Did you run it again?
Yes. So
Repeat the question.
yes, sure. So the question is that whatever the advices we have got, whether we have implemented in the workload and whether we saw the differences, right? So yes, so based on these advices, we saw that the workload was doing aggressive read ahead. It was trying to bring a lot of pages into the page cache, and then there was a latency. It was doing some IOs, and certain point of time, those IOs were taking a lot of time. And those pages were kept in the page cache. And later on, after that, those pages were accessed. So we kind of know that, okay, before doing an IO, we should get the pages which we need instead of getting the entire bunch of pages. So we did call the will need to get that pages. And before doing an IO, free those pages. And it did show that our access time was improved. Whatever we were bringing in the page cache was accessed in a shorter duration, and that is very important.
I'm curious, what was the answer to that question you have on the bottom there that you didn't show?
Right. So let me.
Repeat the question.
Yeah. So there is a question here that, yeah. So I am using in my workload. So it said that you use will need. So I was already, so there, in the workload, will need was already there. So I'm asking that how does don't need will help here, right? Because I was not using the don't need, I was just using the will need, right? So,
I'm curious.
Yeah. I think I can scroll till here. It's starting from starting. So it told me that, okay, this don't need will help me in avoiding the cache pollution. It will improve the cache efficiency and all.
This is a boring answer.
Right. So, but the thing is, it gives you a gist that, okay, if you have allocated a pages,
Yeah, I know.
you have to free it.
I know.
Yeah.
I was just very surprised when it said your readahead is too aggressive. I thought that was, I did not expect that. This I expected. I'm reading the man page now.
Yeah. Yeah, so in certain cases, when the offsets, when your data set is rich, it does give very good answers. It's just not like a man page. It just tells you, that means in certain cases we have seen that it tells that, okay, from this offset till this offset, you are not accessing the page at a proper time, and this is something you should free. So you're getting an extra information based on your workloads there. Yes, please.
Is it giving you an answer based on a rule of thumb, or is it actually telling you that there's a performance impact?
Sorry, I didn't hear it properly.
Is it giving an answer that's based upon a rule of thumb, noticing that you're doing the read ahead too early? Or is it also saying that is it actually telling you that there will be a performance improvement if you change that?
Right. So the question is whether it is just telling you that based on some rule of thumb that we are doing an aggressive read ahead, but whether it is also telling you that with these strategies the things will improve. Is that the question?
Yes.
Okay. Yeah, so when we created the prompt, we told how the data structures looks, what is the algorithm behind the read ahead, right? And based on those information, LLM has made certain suggestions to us, right? So that is the facts which LLM had. Now, whatever the data set we are having with us, that will contain the information very specific to the workload, right? That, okay, I'm reading from this offset to this offset, maybe very aggressively, but there are certain pages I'm accessing after a long time, or maybe I'm not accessing at all. So all this information can be tweaked based on the workload itself. Is that right?
It's kind of depending on the LLM and the prompt.
Yes, yes. Yes, and we can always fine-tune these things accordingly also. Means the LLMs and all. Right, right. So the question is that without LLM itself, can't we just look at the logs and decide the things? Of course, yes.
And apply it with the EBPF. Can we apply it? Can we inject them into the EBPF? Can EBPF modify our runtime application and change advice?
Okay, so that is the thing which is not there right now. So there is some work going on in IO using an EBPF where you can at a runtime modify the things. Right now it is not there, but that is something the community is working on. But to answer your question, yes, of course, we get a histogram, we get a data, and we can look at the data and find out what is going wrong and not. But at a certain time, this data can be huge. You're having large number of data sets, and you are getting these data sets at the various intervals, right? So this assistant can help you in narrowing down the stuff.
Yeah, it will advise the application is the best thing to do, but even this may not be suitable for all of the.
Yeah, maybe, and maybe not. Yeah, but the thing is, it's a kind of assistant with you, which is helping you in narrowing down the problem. Yeah. Any other question? Okay. Thank you so much.